All right, so we're going to talk about a new notation today, and it's just integral notation. We've already done this. We've already done Riemann sums and taken the limit as n goes to infinity. Don't worry, we're going to practice some more today, but we have done that. So this is just a new notation for that process. So it's just saying the integral from a to b. So that means, if like what we did yesterday, we had the graph of 1 plus x squared. So we had this function. And if I wanted to find like the integral from a to b from 0 to 5 is what we did of the function dx. So in other words, it's a way of, I don't like to say it's directions because it's not. Each one of these pieces has a very important part in the formula. But basically it's just saying this is telling us that we're going from 0 to 5. So we go from 0 to 5, and that we're finding the area bounded by the curve between there and the x-axis. Now, you might ask yourself, what happens when the curve goes above and below? Because our y values will be negative on this part of it, which would get me negative area. Well, what we can think of is that this is the net area. So, yes, this is positive and this is negative, and when we add those together, we're going to get their difference. That is okay. So it is okay to get a negative area in this case. All right, so I moved that up here, and if we look at our next example, this tells us to express this limit of this Riemann sum as an integral. So using our new notation, if this is the interval we're going over, with our new notation, it just starts at 0 and goes to pi, and then it's f of x. Well, if you notice, here's our f of x, only it's done in terms of xi. And when we go write these, it'll make a little more sense why. So basically what we do is we kind of just drop the xi, and we say that it's the function x cubed plus sine x. And then we translate this change in x, we translate that as dx. So this would be our Riemann sum written in integral notation. All right, so we can estimate, which is what we've been doing with our left and right and midpoint rule and getting so many rectangles, or we can find the exact answer by coming up with a Riemann sum and taking the limit as n goes to infinity. So looking at this guy here, the first thing that we always want to do when we're doing these, and we're going to do the exact answer in this one, is we want to find our change in x, just like we did before. And our change in x is always going to be basically this part of the integral. So it's our starting and ending points. So we just take 3 minus 0 over n, because we don't actually have a number for infinity, so we're not going to divide by infinity until we're at the very end of this. So our change in x in this case is 3 over n. And kind of the change in x formula, the way that I like to think about it is b minus a over n is always your change in x formula. Okay, so we have 3 over n is our change in x. And then we also need to find our xi, because if you notice in our definition for an integral with the limit of Riemann sum, there's always an xi. Well, xi is it's going to be your x with how x will change as it's in the Riemann sum. So, I can try and explain all of this to you guys, but I'm going to do that in class. For the sake of this, since you'll be watching this more if you just need the help, basically, the formula for xi is just your change in x times I plus whatever a is, whatever your starting point is. So in this case, our xi is going to be our change in x, which is 3 over n times I, and plus 0, because that's the a right here in the integral. And obviously we don't need to write 0, so we do 3i over n. All right, so now we're ready to go ahead and set up our Riemann sum with limit. So we have the limit as n goes to infinity, because again, we want to use infinite rectangles. And that's of our sum from 1 to n, because we want to use, again, infinite number of rectangles. We don't want to limit that. And in this case, our function, if we go ahead and write our function, we had x cubed. Well, we're going to make that our xi cubed minus, we had 6 times x. So again, we're going to make that our 6xi, and then we have dx. Now we can do more with that, because it's the limit as n goes to infinity I equals 1 to n. And this time I'm actually going to replace the xi with what we found xi to be. So we have 3i over n cubed, I don't know, that's supposed to be cubed up there, sorry, minus 6 times 3i over n. And we also know our dx. Our dx is 3 over n. All right, now we're going to go ahead and simplify as much as we possibly can using our different Riemann sum formulas that we've derived, and then our very last step is going to go ahead and evaluate the limits. So I'm just going to do some simplifying here. So again, I have the limit as n goes to infinity, and I'm going to go ahead and distribute this to both things and separate the Riemann sums at the same time. So I'll have 3 over n out front of both Riemann sums. So I equals 1 to n. And this first one is going to be 27i cubed over n cubed, because I went ahead and distributed this to all three of those. All right, minus 3 over n, because again, I have to make sure this gets distributed here. The summation I equals 1 to n of 3i over n. All right, and that's what I'm going to be taking the limit of. All right, I'm going to go ahead and move this up here so we have a little more room. And I'm going to do a little more simplifying as we go. So we talked about this before, that this Riemann sum, I is the variable. That's what's changing. So technically, the n is considered a constant, so we can treat it like a constant and pull it out until we do the limit. So I'm going to go ahead and factor out of this first one, I'm going to factor the 27 over n cubed outside of the Riemann sum. So that'll get me 3 times 27, which is 81, I cubed over n to the 4th, and then I have my Riemann sum. And I wanted to do that because now if you recognize this, this is one of our formulas that we know we can substitute with n's. All right, so I have minus 9 over n squared, sum I equals 1 to n of I. And again, hopefully that's one that we recognize, and that limit is still being applied to all of that. Okay, so now it's just time to go ahead and replace both of these summations with what we have already proven and found. If you remember the staircase problems that we did and stuff, we already know what these both equal. So I'm going to have the limit as n goes to infinity, and I have 81i cubed over n to the 4th. And then I cubed, we know the summation from 1 to n of I cubed is n times n plus 1 over 2, the whole thing squared, minus, and then I have 9 over n squared, and again, we know the summation for I is just n times n plus 1 over 2. All right, so we've eliminated the summations, and now if we do a little more reducing, we'll be able to go ahead and take the limit. These are very lengthy problems. They take up a lot of space, and I'm going to show you a way to do this without having to do so much work pretty quickly. All right, so we have limit as n goes to infinity. I know that this 2 right here can be distributed here, here, and here. So this is really n squared over n, or times n plus 1 squared over 4. So knowing that, I can do some reducing. The 81 over 4 won't reduce, but this n fourth here can go to n squared with that n squared, leaving me n plus 1 squared over n squared. And then minus, and same thing here, I have this 9 over 2 out front, and this n squared can cancel with that n, so then I'm just left with n plus 1 over n. And now if you remember when we apply the limits to infinity, we'll have 81 over 4, and this guy, if we apply the limit to infinity, well, we just know that it's going to go to 0. Sorry, it's going to go to 1. Sorry, it's going to go to 1, because technically the leading coefficient here is n squared, the leading coefficient here is n squared, so we know that we can just reduce those or just have the coefficient, which will just be 1. Similarly, this is 9/2, and so leading coefficients agree here as well, and they're both 1, so that's times 1. And so I just have 81/4 minus 9/2, and And if you do that on your calculator, you get negative 6.75. So that would be the exact area under the curve. And just for a little side note, the reason, just a reminder as to why n plus 1 over n goes to 1. So we're going to come over here and do this. All right, if you remember doing this before, we always divided everything by the highest degree of both parts. So this will become 1 plus 1 over n. This will become 1. And then we go ahead and substitute back in the infinity. And basically everything that's over an n goes to 0. So we're left with 1 over 1. All right, we're just going to practice setting up the expression for this one because we're not ready to solve this yet using Riemann sums. So we're going to do, remember our first step is change in x. So our change in x is always the 3 minus the 1 over n, or 2 over n. And then we always find our xi, and remember our xi is always our change in x times I plus our starting point. In this case, it's not 0, it's 1. All right, so we're ready to go ahead and write our limit. We have the limit as n goes to infinity, and then our Riemann sum. Since we're doing right endpoints, that's what I'm always using with this. We always start at 1 and go to n. I'm doing right endpoints. So we would have e to the xi, and then change in x. So if I go ahead and write that, I have the limit as n goes to infinity. And I'm going to go ahead and put my xi out in front because I just always like, or sorry, my change in x out in front. I always like to do that. And then I equals 1 to n. And if I go ahead and replace the xi with what xi is equal to, I get 2i over n plus 1 for the exponent there on the e. And that would just be rewriting it as a limit of sums. All right, and in your packet you guys have this page of properties of integrals, and I just really want you guys to study it and look at it, but I mean it's pretty basic. A lot of this stuff will look the same as what we've seen before with different things. Like for instance, number 2. It says that if you're adding two functions together, you can actually do the integral separately and then add what you get for those integrals. If you have a constant in front of a function, you can pull the constant out and then apply the process. So very similar. The only new ones really would be these guys here. This one is saying, if you notice, the only difference here is that we've switched the a and the b. So if we switch around the a and the b, we actually get the negative answer. We get the opposite answer. And obviously if we go from a to a, that means there's no width, because I'm starting at my ending point. So that's why that would have 0. And then the other thing is, this next one is saying if I go, so if you think about a curve, it's saying to find the area under this curve. So I've got this curve going on. All right, here's A, here's C, and here's B. So it's saying you can find the area from A to C, you can find the area from C to B, and then if you add those two together, you actually get the area from A to B. So that's what number 7 is translated as. All right, good luck with your homework. Come on in and see me if you need some help.